I will tell you a little bit about theory, and in particular about density functional theory for ensembles. So I will come back to this concept of ensemble. And more specifically, I would like to tell you about a very particular kind of electron correlation effects that does not exist in regular ground state DFT. And that is really specific to ensembles. And that is called density-driven correlation. All right, so how to explain ensemble DFT? Well, probably the best thing to do is to start from what everybody knows, which is like regular DFT, ground state DFT. So as you know, DFT is a ground state theory. So you can evaluate variationally the ground state energy of any electronic system from a density functional formalism. And as you all know, the central quantity in DFT is the famous exchange correlation functional. And basically, so the functional and its derivative, so the exchange correlation potential, that come into play when you solve the Kohn-Sham equations, okay? So that's the standard thing about DFT. So basically, ensemble DFT is an extension of this to a collection of ground and excited states that you are free to choose yourself. So in that spirit, it's very similar to the state averaged KCCF, okay? And the idea is that you assign weights to both the ground and the excited states, okay? So this theory has been written by Gross, Oliver, and Kohn, and initially Teofilou for equi-ensembles. And the basic idea is that rather than looking at the ground state energy of your system, you try to describe the ensemble energy, which is just a weighted sum of ground and excited state energies, okay? And that ensemble energy, which is the analog of the state average energy in KCCF, is in principle a functional of the ensemble density, which is the weighted sum of ground and excited densities. All right, so if you try to compare ensemble DFT and regular ground state DFT, well, the equations are very similar. The only thing that is really different is the fact that the exchange correlation functional is, of course, a functional of the density, but it's also a function of the ensemble weights that you have assigned to the states that belong to the ensemble you're looking at. And this is very important because you will see later on is that the weight dependence, okay, that in principle should be incorporated into the functional, will play a crucial role when you will try to evaluate, in particular, excited state properties like energy, okay? And this is actually the bottleneck at the moment, I would say, in the construction of density functional approximations for ensembles, but I will come back to this. So the Kohn-Sham equations are basically almost identical to the regular ground state DFT Kohn-Sham equations. The only difference is, again, that the exchange correlation potential in principle depends on the ensemble weights. And most importantly, now what you plug in into this potential is the ensemble density. Okay, so that's basically the weighted sum of the ground and the excited Kohn-Sham densities. Another way to look at that is just to say that you are doing a DFT calculation with fractional occupation numbers, and the fractional occupation numbers are controlled by the ensemble weights, the WI weights, okay? All right, and but what's really interesting about this approach is that if you differentiate the ensemble energy with respect to the ensemble weights, you have access in principle exactly to the excitation energies, which is what you are really interested in fact, okay? So that's the kind of formal beauty of this approach. So all of this is in principle exact, and in terms of computational cost, you would say, well, that's basically the same cost as a regular DFT calculation. So getting this kind of method working efficiently, I mean, as a computational cost, would be just fantastic, because you would avoid the additional computational costs that you have, for example, in TD-DFT. So you would not need any post Kohn-Sham DFT treatment in a way. But of course, if you want to get this working, you need proper functionals. And that's essentially the reason why now ensemble DFT is not used, I would say, routinely. But I think clearly it deserves much more attention that it has attracted in the past years. So what I'd like to tell you about today is specifically the development of functionals for the correlation energy, for the ensemble correlation energy. So how can you design correlation functions for ensembles? Well, one strategy is to recycle the regular ground state correlation functionals, a bit as it's done in the adiabatic eDFT, for example. And here I'm mentioning the work of Michael Filatov, of course, who's really a driving force, I think, in the field, obviously. And so basically what you do there, you write your correlation energy as a weighted sum of individual correlation energies that you compute by inserting ground and excited Kohn-Sham densities inside the ground state correlation function, okay? So when you do this, of course, you should remember that because you are using the ground state correlation functional, so I gave here the formal expression in DFT. And what's very important, of course, is that in ground state DFT, obviously, the two wave functions, so psi of n, which is the true interacting wave function, and the Kohn-Sham determinant share exactly the same density, okay? That's a basic idea of DFT. And that's something to keep in mind because you will see later on that in the exact ensemble DFT, this is not the case, actually. Okay, another strategy that Pierre-François Luce, and coworkers have been trying to explore much more recently is to use uniform electron gas models to design weight-dependent correlation functionals, so LDA kind of functionals. So there you see the strategy is a little bit different because in that case, you basically extract individual correlation energies for ground and excited state from a finite uniform electron gas. But again, in this particular case, so when you are in a uniform electron gas, the ground and the excited states all have exactly the same density, whether you consider the non-interacting Kohn-Sham system or the interacting one. So again, that's important. And that's actually the connection with the previous approximation I talked about. The interacting and non-interacting wave functions will have the same density, okay? So that's a kind of common denominator to these two approximations. Now, the question I'd like to raise, and this problem was mentioned for the first time, I think, in the literature by Gould and Vitalis, is this correct? I mean, if you refer now to the exact theory, is this procedure, this way of constructing correlation functionals, okay? And if not, where is the problem? So in the exact theory, you can actually write the correlation energy of your ensemble as a weighted sum of individual correlation components that I wrote here. But the substantial difference between what I told you before and now the exact theory is that, so you have the true interacting state, psi I, okay? And then you have the Kohn-Sham determinant. But in ensemble DFT, you ask the theory to reproduce the ensemble density, which means that you only expect your Kohn-Sham system with the Kohn-Sham wave functions to reproduce the ensemble density. In other words, the weighted sum of the Kohn-Sham densities should be equal to the weighted sum of the true densities, okay? But which obviously doesn't mean that the densities individually are equal. So there's no reason to believe that the Kohn-Sham determinants have exactly the same densities, okay? And that's where the problem is. So in other words, in the exact theory, when you evaluate a correlation, an individual component to the correlation energy, well, the interacting and the Kohn-Sham wave functions do not have the same density. And this is a major difference between ground state DFT and ensemble DFT. So now the question is, how should we correct for this? And because the approximations, the usual approximations do not take this into account, how can we actually correct the functionals, okay? And another question, obvious question is does it really matter in practice, okay? Should we worry about this? So Gould and Vitalis proposed to split the correlation energy of each individual states within the ensemble in two parts. So this density-driven correlation thing I was telling you about at the beginning of the talk is actually coming from that observation, okay? So what they did, they say, okay, well, if we try to connect the usual approximations to the exact theory, one way to do that would be to introduce additional Kohn-Sham wave functions. So these are denoted as so phi I bar on the line here on the slide. And the idea is that then you would create these Kohn-Sham wave functions, which would have a property to have exactly the same density individually, okay? And then you would basically evaluate a first correlation energy, where these guys have exactly the same density, and you would call this state-driven correlation energy, all right? But of course, this is not the correct correlation energy component, as I told you before. So you need a correction. And this additional correction, which is written here, is basically what they called at the time density-driven correlation. Okay, so that's a way basically, and the idea is to say, okay, this density-driven correlation is basically absent from standard approximations. So you should find a way to model this contribution. Okay, so this is supposed to be in principle exact, but for sure in practice, and also at the exact theory level, this raises many questions. Well, first of all, you have to design a Kohn-Sham, an excited Kohn-Sham system, for example, for a given excited state. So you have additional work to do, and you're actually not sure, and in general, they are not unique, these Kohn-Sham determinants for excited states, because you don't have a Holmberg and Kohn theorem for excited states in general, I mean. So that's the first problem. But so you're not sure that these Kohn-Sham wave functions are unique. And you may actually get also V representability issues. So for example, there are some simple models where you cannot apply this decomposition, okay? And I would say most importantly, you have no idea how you're gonna model this. If you want to design a density functional approximation, how you're gonna basically construct this contribution. So that was somehow the disappointing part of this work, is that it was not clear how we could basically design functions for this. Okay, so what I basically proposed is to proceed a little bit differently, and instead to look at the exact individual correlation energies, which I denote here E, but without the calligraphic font, so you will see why. So before I was talking about the components, okay, and which contribute to the ensemble correlation energy. And now what I'm saying is, like, instead of doing that, we may actually evaluate directly the exact correlation energy. And again, the weighted sum, of course, are the same, but it doesn't mean that individually these two correlation energies are the same. They're not. And the reason is, I gave you before, is that the Kohn-Sham determinants in the ensemble picture do not reproduce the exact densities. So in fact, in the exact correlation energy of a given state, you have a contribution that will update the density so that you recover the exact nuclear potential energy, for example. Okay, so this is a different way to proceed. And so why is that interesting? It's because you can actually extract exactly the individual correlation energies directly from the ensemble. Why is that so? Because the ensemble energy is a simple linear function of the weights. So you can actually benefit from this. And this is what I'm writing here. So just based on the fact that your ensemble energy is linear, you can really express, so you have an explicit connection between these individual components I was telling you about and the exact correlation energy of a given state, okay? And you get something that looks like what you have here on the slide. So you see explicit dependence on the weights, and most importantly, you also see derivatives with respect to the weights, which I told you are important to extract individual properties. So what can we do with that now? Okay, so what you realize is, if you are interested in a given state J, okay, so you have this individual component first, but then you have other contributions that come from all the other states that belong to the ensemble. So then what I just did, I said, okay, rather than introducing additional Kohn-Sham wave functions, what I can just do is read this formula and separate contributions. So what I'm going to do is just read what I will call later on the state-driven correlation and the density-driven correlation, which is what I did. So if I look at state J, for example, I can say, okay, all the contributions that come from state J, I will call them state-driven. So I'm considering a specific state and say, okay, these contributions belong to the state. And this is what I will now call the state-driven correlation energy. And then the other remaining contributions that I can read here, I will call them density-driven. So again, I have this separation. It's in principle exact. And again, I do everything from my ensemble Kohn-Sham system. So I don't need to introduce anything else to get these contributions, okay? But what's really interesting is once you've done this, you can actually express exactly a density-driven correlation energy. And this is what you have. So why is that interesting? Well, you see that now I can evaluate this quantity in principle exactly and explicitly, more or less, because I see the weights appearing explicitly. And now you see that these density-driven effects that we are talking about are in fact related to the linear response of the Kohn-Sham determinants when you slightly change the weights, okay? So this is basically what is completely absent from standard density functional approximations in ensemble DFT calculations. So if you want to evaluate this contribution, well, you have to get this linear response. So it's a static problem. So it's easier than what you would have in TD-DFT. And either you can get it with finite differences, or you may solve a couple perturb Kohn-Sham equations, for example, okay? So, but that's basically a way to evaluate this density-driven correlation. Okay, now comes the question. Now that I have defined this correlation energy, is it really important? Should we really worry about this? Okay, so the conclusion of Gould and Pitali's work, even though we use a different decomposition, their answer to that question was definitely yes. We should worry about this, and we should clearly find a way to describe this correlation, okay? So what I did, I just considered a very simple model to try just to see if indeed it matters or not. So I consider here the very simple Hubbard dimer, which is just a prototype for a diatomic molecule. And so in this case, what matters is the 2-electron repulsion U on the atoms. And here I will consider a strongly correlated limit. So I will assume that it's quite large, okay? And then I have also a potential, delta Vx here, that allows you to introduce asymmetry in the model. And I will consider a weakly asymmetric situation. So in this particular regime, I just want to see what happens. And in this model, the density is just the number of electrons on a given atom, okay? And the whole system contains 2 electrons. Okay, so what you see here on the screen are the state-driven and density-driven contributions to the first singlet excited state. So on the y-axis, you have the weight. So you have when the weight is 0, this is just regular DFT, okay, ground state. And then when it's 0.5, this is the equi-ensemble. So what you see immediately is that basically the state-driven matters as much as the density-driven. So it's not negligible at all. And it's very striking, of course, when you stand here in the equi-ensemble case. You see the ratio, this is 3/2. And that's actually exactly what Gould and Pitalis observed on a different model, okay? So it's not a little detail. It seems like it's really, we should really worry about this. And of course, you may also wonder, but all in all, when you evaluate the ensemble correlation energy, does it really matter? Because previously here, I was just showing you what happens for the excited state. But now if you do the state averaging, what you get here, so the 0 on the y-axis would correspond to what happens in the symmetric dimer, okay? And now we are looking at deviations from the symmetric dimer. And again, what you see is that basically the total ensemble correlation energy is not varying that much. You see, the variation, the deviation from the symmetric case is not that significant, but there is a kind of compensation between the state-driven and the density-driven correlation effects. So if you have the state-driven without the density-driven ever, you may be completely off, okay? So, so again, the idea is to say, well, maybe we should look at that more carefully. Okay, so with that, I'd like to conclude the talk. So I think you got the message. Many-electron ensembles exhibit a very particular type of correlation effect that again do not exist in regular ground state DFT, and these effects are called density-driven. One important thing now is that I think we have a way to evaluate them in principle exactly, because we have a formula. And we know how we can get them from the linear response of the Kohn-Sham determinants within an ensemble, which is kind of nice. I've shown on a very simple example that these effects can be substantial. Obviously, now we should test that on ab initio system and try to see if really this is very substantial in realistic systems, okay? And one last thing I'd like to say is that I focused here on neutral excitations, but in fact, we have recently